Good afternoon, everyone. My name is Eileen Tanghal. I am a senior partner at In-Q-Tel. In-Q-Tel, we are a technology scout and investor on behalf of the U.S. intelligence community. And myself and Lieutenant Colonel Greg Van Dyke are happy to talk to you today about microelectronics in advance of the workshop tomorrow. So let me just advance. Thank you. So microelectronics, just a definition, really are small electronics that are made on semiconductor materials comprising transistors that are put together to form integrated circuits. I think most of us know that microelectronics actually underpin most technology revolutions. All the technologies that you can think of today, everything from the computer to the phone to this Zoom meeting, are really only possible because of microelectronics. In the defense sector, all the advanced defense systems, including hypersonics, navigation systems, and missiles, are all dependent on microelectronics. If we look at the microelectronics cycle today, we see that it's effectively very global. While the US really dominates on the design and really on also the manufacturing equipment to make microelectronics themselves, most microelectronics are actually physically produced, packaged, and assembled in the Asia Pacific. Now, if you look at what it takes to actually create a microelectronic product, it's highly, highly complex. In fact, there's one SIA study, so that's the Semiconductor Industry Association study, that says one large semiconductor microelectronics maker can have as many as 16,000 suppliers. So what this means is that this complexity really creates a large attack surface. And there's three areas where microelectronics themselves, as they are produced, can be attacked. First is in the pre-silicon era. So the pre-silicon era is really when a chip is still in the design phase. So this is digital blueprints, CAD files, specific documents. Here, invasive attacks can really change the digital layout of the chip. There could be untrusted chip designs called IP that are introduced, Trojans, kill switches, backdoors, and control circuitry that could be introduced. And the second category, in silicon, this is really when it's being produced. So there's usually a mask as well as fabrication. This is what I was saying, it was effectively done in Asia Pacific. Here, in silicon, attacks can happen to alter the physical layout of integrated circuit, attack the production tools to cause process failures, etc. The third category, and this is the one that really is one that's seen within the DoD and the government as perhaps the most worrisome or the most vulnerable. This is associated with the packaging, testing, and development of finished chips. This is most readily easily attacked. Here, you can have theft of original components, swaps, counterfeit of untrusted components, or falsified testing to pass certification. Historically, we would look to large companies, but really the innovative smaller companies to really help defeat some of these attacks, as well as come up with new innovations to really place the US ahead of our competitors when it comes to microelectronics. But if you actually look at what's going on in the semiconductor and venture capital world, we see that in 2019, out of all venture capital deals done, only 0.5% were done in semiconductors. If we look at the deals in the US compared to those being done in China, we see that it's about half. There are 167 deals that were invested in China and just 85 in the United States. More worryingly, despite the fact that capital is readily available in the US, we can see that the mean China deal in semiconductors received $29.9 million, whereas the US companies received just 11.4, so that's about a third. And the same is true for the median, 14.7 versus 4.0. During tomorrow's workshop, we hope to discuss solutions to some of these problems, and now I'd like to hand it over to my co-presenter, Lieutenant Colonel Greg Van Dyke. Thank you.
Thanks, Eileen. Yeah, and this collaboration between industry and government is absolutely critical to solve our most complex national security needs. So in two charts, I'm going to tell you, hopefully convince you the importance of microelectronics, and then talk to you about specific challenges and then how that may frame the discussion for tomorrow. So overall, well, why do we need these? Well, as we shift to great power competition with technologically equal, hopefully never more advanced adversaries or competitors, technology really leads to military dominance. And at the end of the day, it's the guts that count. And maybe I'm a little bit biased, but if you look at the F-35 as a case example, those 24 million lines of code, which that was a couple years ago, there's probably many more lines of code. It's the sensors on board that platform, how it takes that information in, processes it, and then gives it to the pilot to make choices in the battle space. And so that type of data fusion is ubiquitous across national security needs. And unfortunately, current weapon systems have 10 to 20 plus year old technology. Now, I'm not saying that every system needs to have state-of-the-art capabilities, but a wide swath of them does. And if you want to think about it simplistically, going back to whether it be our squadron officer school or whatever professional military education that you've had, it goes down to the OODA loop: observe, orient, decide, act. And whoever can compress that OODA loop and run those cycles faster than the adversary will win the battle. And that's exactly what microelectronics allows us to do, okay? And so it is absolutely the bedrock for all of the national security systems, not just the F-35 that we talked about here, but hypersonics, 5G, artificial intelligence, missile defense, autonomous systems, space systems. I mean, it really is everywhere. And it's not just us that are trying to play in state of the art. As you can see in the chart on kind of the middle left side with the white background, that's a look at the companies that are producing at state-of-the-art technology nodes. So the smallest nodes commercially currently available in the commercial space. If you look in 2007, there were 13. As we get down to now, down to 7 nanometers, there are 3 in the world, 3 companies, and only one of those companies is US owned. Now, an even more challenging part of that is you see SMIC. So in the line, it says diminishing friendly supplier base with China rising. So SMIC or SMIC, how some people pronounce it, recently blacklisted by the US government. You better believe that the Chinese are going to have these advanced capabilities. And so if we want to stay ahead of those technologically advanced near-peer competitors / adversaries, we have to invest in these capabilities. And at the end of the day, it's about taking a bunch of data, fusing that together, processing it, and making a decision for either a human in the loop, say a pilot in a fighter aircraft, or in autonomous systems. And so really is the bedrock, and it is something that we really have a lot of challenges to getting there. And so if we go to the next slide, we'll talk about exactly why there are such significant challenges. So I like to split it into 2 broad categories. Now, these are just kind of my categories, and so some may quibble on which, where they fall or whatever, but it's just something to keep in mind. So I lump them into system requirements, and these are unique system requirements for national security applications. And then there are some supply chain considerations. So let's talk about the unique system requirements first. So we have very unique applications. I don't think that's anything people would debate about. We have unique sensor fusion requirements, unique artificial intelligence, could lead to very advanced packaging designs that are not commercially, that is not a commercial product for commercial applications. Secondly, we have unique environments, whether it be radiation hard, unique temperature variations or ranges, vibration, shock, etc. We have the need for very high reliability systems, such as nuclear certification or other critical systems. Now, there are some corollaries in the commercial space, say for aircraft systems or autonomous vehicle systems. But some of our systems even have more harder requirements than those. We have very long lifetimes generally in the systems that we put out in the field, and these can be multi-decadal. And so having that high reliability over those lifetimes is something that the commercial industry just is not used to. Security, obviously. I mean, we have state actors that would absolutely love to infiltrate and put malicious code into and designs into some of our systems. And really, what Eileen talked about, we have to not simply think of this as a fabrication facility view. And that's what's kind of been done in the past. Really, it involves everything from design to those automation tools, all the way to the end product going out the door to that DoD prime contractor to be put in to an overall system. We have very long system development and production timelines, and so that can lead to the need for long technology freezes, which is not necessarily typical in a lot of commercial fabrication facilities where process changes are tweaked to enhance the performance for commercial needs. Those tweaks, while they may be advantageous for commercial applications, may not be for things that we care about. Okay, so down to the supply chain challenges. I'll tell you what, international traffic and arms reductions, export administration regulations, ITAR, EAR, is a significant challenge right now for us to source state-of-the-art components that we need for our systems, and that is being actively worked, and we need to put a lot of emphasis on that. Obviously, it's a very complex situation. You have the Department of Commerce, you have the Department of State, DoD, DOE, and NSA, and so those discussions are happening right now. We have very low quantities that we need for our systems. I put less than 1% as just a generic baseline of the market. And so if you're a commercial vendor and you're producing trillions of components for, say, smartphone applications, getting a couple mask or a couple of wafer orders may not lead to a strong business case for you to do work with the government. There are significantly high input costs to this business. I didn't put the specific numbers in here because it depends on the company, and I didn't want to give away any company proprietary information. But shuttle runs in particular, so this is actually getting product back from a fab, can run in the millions. Design tools can run in the millions per year. One fabrication tool itself is hundreds of millions of dollars. And so that can be a significant impediment for national security applications, especially when you think about the low quantities that we need. Obviously, overseas production, Eileen touched on that a little bit. US is 12% and decreasing, East Asia is 75% and growing. And limited manufacturers, I mentioned it in the chart below, that right now, only one example, there are many examples throughout, but I only touched on state-of-the-art technology nodes where there are only 3 companies in the world that are at state-of-the-art. So all of these challenges are things that as we go into tomorrow, that to keep in the back of your mind as we discuss various ways to form this prime initiative. Overall, we have 2 large topics that these kind of fit in that we'll be discussing tomorrow. One is supply chain access and trust, The other one is innovation. And so most of these, if not all of these, you can find a place in those two overall topics. So we really look forward to this. Eileen, hundreds of people in this community strongly believe that getting state-of-the-art capabilities into our warfighter hands for microelectronics is going to be the key to defending against near-peer adversarial challenges. So with that, I will turn it back to our AFWERX host. Thank you.
Thanks, Greg. Appreciate it. Well, thanks, everyone. That concludes our webinar for today. If you want to go back to AFWERX.com, we're having concluding remarks on the day. But thank you to all our panelists here. We greatly appreciate it.